Hello everyone, let's analyze. So we're going to talk about the real line. A lot actually. But first, we're going to build it. So our goal for today is to build the set of real numbers using the fewest possible set of rules or axioms. And we're going to begin that process by defining a field. So a field is a set F imbued with two arithmetic operations, addition and multiplication, meaning that any two elements of the set F can be added to yield another element of the set F, and any two elements of the set F can be multiplied to yield another element of the set F. And these two arithmetic operations have to follow certain rules. Rules that, well, frankly, we're actually really familiar with because we've been adding and multiplying for quite a while now. So one of those rules is associativity. A plus B plus C yields the same result as if I added B plus C first and then added A. Similarly with multiplication, A times B times C is the same thing as multiplying B times C first and then multiplying by A. Again, this is something that we know, but remember that we're going to build the arithmetic and the set of real numbers from the ground up. So we have to be specific with these definitions. There's commutativity, that addition and multiplication is essentially symmetric. Now, of course, as we go this, we might want to compare these rules to other arithmetic operations and other types of sets. You may recall from your linear algebra class, for example, that you don't have, in general, commutativity of matrices when you multiply them. Right? This is something that you do have for a field. Distributivity of multiplication over addition. In other words, I can distribute the multiplication over a sum. A times the sum of B and C is the sum of A times B and A times C. And then there are the identities. And as we have two arithmetic operations, we actually have two types of identities. There's the additive identity. A plus the additive identity is A. Of course, if I said A plus a mystery number is equal to A, we would know that that mystery number would be 0. And in fact, 0, or sometimes called O, is the additive identity. And then there's the multiplicative identity. It's an element of my field such that when I multiply A times it, and A is any number, I get A. Of course, if I told you that A times a mystery number is A, we would know right away that the mystery number is in fact 1. Now, additionally, as an axiom, in other words, by definition, the multiplicative identity and the additive identity cannot be equal. Okay, they cannot be equal. So the multiplicative identity does not equal the additive identity. In other words, 1 is not equal to 0. Now, again, we might think, well, sure, of course not. But remember, we're building this from the ground up. What if I didn't require that 1 cannot, by axiom, equal 0? What would happen? Could 0 on its own be a field? You should think about that. Okay, now there are the inverses. And again, because we have two arithmetic operations, we have two types of inverses. We have an additive inverse. So A plus the additive inverse equals the additive identity. Now, of course, remember the additive identity is 0. So the additive inverse to a number A is just, it's negative, right? So a plus negative a is 0. In other words, for every number, I can flip the sign. Flipping the sign on a number gives me the additive inverse, because when I add a number plus the flipped sign of itself, I get the additive identity. That is 0. And of course, we should note that this defines subtraction for us. Right? A minus b is essentially a plus the additive inverse of b. Now, there's an additive inverse. There's also a multiplicative inverse for all numbers except for the additive identity. In other words, except for 0. 0 has no inverse. Okay, what is the multiplicative inverse? Well, it's the number that when multiplied by a yields the multiplicative identity, that is 1. So a times its multiplicative inverse, which we might know by another name as the reciprocal, is the multiplicative identity, which of course we know is 1. So a times its multiplicative inverse, which again is just another word for reciprocal. A times its reciprocal is 1. And every number has a multiplicative inverse. That is, every number has a reciprocal except for 0. And of course, we'll observe that this defines division for us. A divided by b is really just defined as a times the multiplicative inverse of b, which is why no one can divide by 0, because a divided by 0 is defined as a times the reciprocal of 0, and well, by axiom, 0 has no reciprocal. So you can't divide by 0. Not even Chuck Norris can do it, despite what you may have heard out in the streets. Okay, those are the axioms for a field. Is that enough? Did I do it? Have we built the real numbers? Well, let's consider the following questions. Is the set of integers a field? Is the set of rational numbers a field? Is the set of 4 elements, 0, 1, a, b, a field if I define addition and multiplication according to the following tables? Right? Do those tables and the way they define addition and multiplication satisfy all of the axioms of a field that I just went over? No, yes, yes are the answers to those questions. Oh, by the way, you can prove that. I'm certain of it. You could do it. You should do it, in fact. It'd be a good exercise. This leads us to the conclusion that the field axioms alone just aren't enough, because we actually can have a 4-element set that satisfies the field axioms. We need more. Now, before we continue with the additional axioms we need in order to build the real line as we know it, we need a few further basic properties of addition and multiplication, but they're not axioms because they can actually be proven from the axioms we just discussed. So here's one. For all numbers in a field, if I multiply that number times the additive identity, in other words, 0, I get 0. So that's not an axiom. It's not by rule that a times 0 is 0. It's something we're going to prove. So to prove it, we would need to show that a times 0 is the additive identity. In other words, a times 0 plus some number yields that same number. So let both a and b be elements of f. A times b is a times b plus 0. In other words, b and b plus 0 are the same thing because 0 is the additive identity. And because I can distribute multiplication, this is a times b plus a times 0. So a times b equals a times b plus a times 0. Therefore, a times 0 is the additive identity. Meaning a times b plus a times 0, or 0, is a times b. We've proven our result. Okay, here's another. We had mentioned that to flip a sign on a number is to give the multiplicative inverse. That's the same as multiplying a number times -1. Not by axiom, rather this is something that we can prove. So we need to prove that if I multiply -1 times a, what I get is the additive inverse of a. In other words, a plus -1 times a yields the additive identity, or 0. Well, that should give me 0. Does it? Well, again, we know right away that a plus -1 times a, of course, is 0, because we've been dealing with real numbers, well, ever since we asked for 2 cookies when we were about 1 or 2 years old. However, let's justify each step of our proof using the axioms or any previous lemmas. We know a times 1, by definition of the multiplicative identity, is a. So a can be replaced with a times 1. And then I can factor out a using the distribution of multiplication over addition. Now, 1 plus -1, well, -1 is the additive inverse of 1. So the definition of -1 is the number that when added to 1 is 0. So 1 plus -1 is 0, and I get a times 0. And of course, a times 0 is 0 because, well, we just proved it. That was lemma 1. Therefore, -1 times a is the additive inverse of a, which is to say it's negative a. Okay, another one. If a times b is 0, then a or b, or both, must be 0. Lemma 4. The additive multiplicative inverse of the additive multiplicative inverse of a non-zero number is that number. In other words, the reciprocal of a is a, and negative a is a, so long as a is non-zero. Also, 0 and -0 are the same number. Of course, you might be wondering, wait, where's the proof? Well, the proof is in your homework once you're done with your homework, because you'll have to prove it in your homework. Okay, now we can get to the further axioms that we need in order to generate the real numbers. So an ordered field, F, satisfies the field axioms. In other words, F is a field. But in addition to addition and multiplication, we also have a less than relationship. And this less than relationship has to satisfy the following properties. One is an invariance under shift. If a is less than b and I add the same thing to both sides, I get the same inequality. Transitivity. If a is less than b and b is less than c, then a must be less than c. The trichotomy axiom. For every 2 numbers in my field, exactly one of the following is true. A equals b, a is less than b, or b is less than a. Only one of those 3 things could possibly be true at a given time. And invariance under positive scaling. If a is less than b and c is a positive number, then a times c and is less than b times c. could we prove that the additive identity is less than the multiplicative identity? Now, of course, we know it's not equal because that was actually part of the axiom. So of course we can. But notice that this is not an axiom, but rather it's a natural result of the axioms of an ordered field. Anytime you have an ordered field, the additive identity must be less than the multiplicative identity. In other words, 0 has to be less than 1 if you have an ordered field. But first, a lemma. If A is less than B, then negative B is less than negative A. In other words, if I have an inequality, taking the additive inverse of both sides, in other words, flipping the sign on both sides, means I have to flip the less than or equal to sign. So let's prove that. If A is less than B, then A plus negative A minus B is less than, and then what happened? Homework happened. But now that we have the lemma in our arsenal, and by the way, you will prove the lemma in your homework, we can prove the theorem that the additive identity is less than the multiplicative identity. So by axiom, specifically the axiom on identities, the additive and multiplicative identity cannot possibly be equal. So let's assume for the moment that 1 is less than 0. But that's absurd. Well, that's actually the point in this case. Our goal is to show that this assumption logically leads to a contradiction, thus proving our result by contradiction. In other words, if we assume that 1 is less than 0, and that implies an impossibility, then it can't possibly be true that 1 is less than 0. And 0 can't equal 1, so by the trichotomy axiom, we would have our result. This method of proof is known as reductio ad absurdum, if you're fancy, which literally means to reduce to absurdity. And if you're not so fancy, it's a proof by contradiction. Okay, so remember, we're assuming that 1 is less than 0. Well, from lemma 5, we had that 0 and negative 0 are the same. And from lemma 6, we have that if we flip the sign, we flip their positions. So if 1 is less than 0, then 0 or negative 0 is less than negative 1, making negative 1 quote unquote positive. Now if I multiply both sides by negative 1, now why can I multiply both sides by negative 1 and not have to flip the inequality? Well, because remember, negative 1 is, quote unquote positive. Negative 1 is greater than 0 by our assumption. Well, 0 times any number is 0. We've already established that in a previous lemma. And negative 1 times negative 1, we've established that that is 1. So if 1 is less than 0, then 0 is less than 1. But that's impossible. The trichotomy axiom forbids the case that 1 is both less than 0 and greater than 0. So our assumption, our absurd assumption, yields an impossibility. Thus, it's impossible for 1 to be less than 0. And since 1 is not equal to 0, the only remaining possibility is that 1 is greater than 0, which is the result of the theorem we wanted to prove. Okay, so is that it? Did we build the real numbers? No, not yet. Because while it's true that we've added more, it's still true that the set of rational numbers, for example, satisfies the axioms of an ordered field. So if we stopped here, then the square root of 2 would be nowhere in our set. The length of the diagonal on a unit length square would not be measurable by a number. Well, that's no good. We need more. We need to fill in the holes in our number line. Well, what do we need? Well, you have to stay tuned for next lecture to find out. That's it for today.